Okay, welcome everyone again. We are in the third session of the day. I hope you enjoyed the lunch. We are a little bit late, but hopefully, so this is the last session of the day. We have after this session the poster break where we can be more socialized and talk between each other. So let's start with the third session with Professor Minghong Yang. Thank you for being here. That is going to talk us about the draw tower, fiber grating array, and industrial application they are working on in his lab, in his building. That building is of his own. So tell us.
Okay. Good afternoon, everybody. First of all, I'd like to thank Natasha and also Carlos for inviting me here. It's a really good experience for me to be here in Pamplona. It's a nice city and nice country. I thank you for your work. So I come from Wuhan University of Technology, Wuhan, China. The topic of my presentation is drawn tower fiber-based grating array and its industrial applications. So I'll have four parts. First, I will make a brief introduction about our institution, and then technology about the drawn tower fiber gratings and such kind of fiber Bragg grating array applications for sensing application, especially for DTS, DSS, DAS. This is the distributed temperature sensing, distributed strain sensing, distributed acoustic sensing. Also, we call it DXS, that's multiple parameter sensing distributor. And also, we have other optical sense research activities. If I have time, I can mention it about. So everybody know about, I think everybody know about China. So China, where is it in the world is clear, but where is Wuhan located? Here, you see the map. This is the map of China, and here is Peking here. And Wuhan just in the middle. Maybe some of the, you know that the very famous river, the Yangtze River. We are just across the Yangtze River, and here is the very big Three Gorges Dam, the world's biggest dam across the Yangtze River. And we have a very beautiful lake also in the city. So our institution is the National Engineering Research Institute on fiber optic sensing China. This is our unique institution. And we have, as you see, this building, it's all the people sitting here is on optical fiber sensing. We have 56 faculty members, and with more than 200 master and PhD students in this building. We don't have a bachelor student, so most of the people here are working research and development R&D on fiber sensing technology. So what we have in the laboratory, we have different machines for microstructuring and also for fiber FBG writing, that's for sure, and also for some kind of coating machines, and also some. Especially, I would like to say that we have the possibility to make the drawn tower gratings in our laboratory. That means we can make thousands, even more than thousands of grating arrays during the fiber drawing process. So in general, we have from the very beginning of the sensing principle and sensing materials, key devices, sensing network, and application engineering applications. We can all make this in our national institution. So, okay, and then I will go to the second part, what's the drawn tower fiber grating. We all know that fiber optic sensing technology can be used in many industrial applications, especially in China. There's a huge market from the structure monitor assay and railway, coal mill, and the bridge, and so on, many industrial applications. Normally, we know that for the distributed sensing, we have the different technologies. One is the Raman scattering, another is Bragg scattering, and the other is the radius scattering. Normally, radius for the fabrication, and the Bragg for temperature and strain, and for Raman scattering, then with temperature measurement. This is based on the multiple, or we call it the distributed sensing. But the question is based on the scattering signal. So normally, scattering signal is very weak, and also you have the no response, and also you have to make a trade-off between the accuracy and the and spatial resolution and so on. Another technology everybody is well accepted is based on the so-called wavelength diffusion multiplexer. This is so-called FPGs is based on different FPG wavelengths, and you can find out the difference from the wavelength shape, and then you can get the signals. The advantage is that it have very strong signal and fast response. You can get a very precise measurement. But the question is that due to the limited broadband, you have the not too much point. You can be used for FPGs, but also typically you have to write the FPG one by one, and then you have to connect all the FPGs by wiring and so on. Then the mechanical robustity is not mechanically robust. So I would say this is for a typical FPG and the diffuse sensing. They have the different properties. For the reflectivity, singular, say for SNR for FPG is good, but for distributed sensing is not good. But the problem for FPG is that you have very point arrangement. You have the networking is a problem for FPGs, but for the distributed sensing, it's good enough. So nowadays, people we can order possibility, including large capacity and also high precision, like long distance and fast response. How can we make that in one? So normally, as we know that for the traditional FPGs, you have to first to remove the coating, and then with the simulator to write the FPGs, and then you recoat the coating. That's actually this is technology. It's good, but well for the large applications is somehow limited. And we have technology in our university that we can make a drone tower grade system. That means we have the preform, and then after the furnace, high temperature furnace, then the free, we can write FPGs during the drone tower, and then with the coatings later on we have the grating arrays. So for such technologies, we have a very continuous FPGs. But just FPG is very weak. It's a weak FPG. For example, reflectivity is normally 10 to the minus 4, even minus 5, minus 6. That is also possible. But this kind, you don't have the spicing point and compared to the traditional FPGs. So this is our facility at our institution, and here somehow the FPG writing systems. So we use at the very beginning we use different technology. First based on teleport technology, another based on face mask technology. For the teleport technologies, you have to make very precise the fringes and the movements of the mirrors. Otherwise, you can have very good design. And later on, we use the UV laser face mask technology, and then we can make the reflective very good for the industry applications. The question is that the fiber itself is moving. It's not stationary. It's moving, and then you have to keep the moving fibers as stable as possible, and then the many technology challenging. How to make the gratings uniform, especially here you can use just a single pulse irradiation. That means because it's moving, you can make multiple exposure, just one single exposure. Here we use the finally we at the very beginning we can make all this like way you can see the reflectivity and the wavelength is not that uniform, and later on you have to optimize the deposition process and also the coating process and so on. Then you can make the very uniform FPG arrays for real applications. This is the challenge, and also how to make the gratings as more as possible And actually, in our laboratory, we can make in one single fiber even more than 100,000 FBG arrays with reflective with insertion loss less than 0.5 dB per kilometers. So okay, we have that. What we can do with this such kind of FBG arrays. So if you want to go to the industrial application, for sure you have to make the cabling. Then we are also can make different cabling for the different applications. For example, temperature sensing cable, and also for the fabrication sensing cable, and also strain sensing. It's based on your application. You have to make the cabling process very specially, and also if there's a point measurement or if there's a single the very critical areas, you can have the special mounting process or protection structure for the coatings. It's for the FPGA arrays. It depends. So now I moved on to DTS technology based on the drone tower. DTS, that's the distributed temperature sensing. We are focused on temperature sensing. Temperature sensing is based on the monitoring for the wavelengths. You see here, this is in this array we have the same wavelengths. That's wavelengths lambda 1. All have the same wavelengths, but the spatially is different. Same, we can use the site based on the time domain reflected singular, and then we can make the different from area to area different wavelengths. This is an example. We have the 3 FBG arrays that's totally reflective, and this is one almost 2,000 FBG in this wavelengths. And then if you locate it in the time spatial, or they can find the different position. You have different wavelengths as you see here. This is that's 2,000 points, and with each FBG spacing with 1 centimeter. That means there's 2 kilometers, 2 kilometers, 2 kilometers. That's totally 6 kilometers with different 3 different FBG arrays. And this is a calibration for such sensors, and we make a demonstration. If we hit this region and we hit this region, then you can find the difference. But in this region, you can keep it a low temperature, and then you can use such sensors for the different temperature measurement. And then we make the cabling with the industry partner, typically for the OPGW cable. This is a very commercial cabling process, and also inside you see that point. This is the FBG points you can see, and we use that for the oil field test. That's the monitoring the downhole temperature for the oil field test. This is just one very simple demonstration. Okay, another demonstration for the distributed strain sensing. For example, we in China there are many huge structures which need to be monitored for the deformation, for the strain. And we make such kind of cable as you see here, this is the cable. In the cable we can make the gratings already pre-strained. Pre-strained, that means you are not loose. You are already know how, and then it's easy to be calibrated, and then we can make such kind of continuously FBG strain arrays. So this is a demonstration for bridge monitoring. For example, there's a 65 millimeters of bridge. We want to monitor the strain of the bridge when the on the working, and then we install the fiber cables along the fiber the bridges, and then we can monitoring the deformation of the strain. Normally monitoring by the shift of the wavelengths. Then at the with the time schedule, and you see what it happens. For example, if we have the loading at different areas, these areas you can see the deformation here, and in these areas you have the deformation there. So this is typically for the bridge monitoring, especially here in China. There are many new built bridges. For the new built bridges, some of them was installed with our FAB cable distributed sensor systems to monitor the structural healthy. You can see here is the test, the field test, and then we want to check how strong, how robust, how strong the bridge is. Then we use different tracks, and then we have different dynamical or statical strain deformation with the different tracks go on the bridge, and then monitor the deformation of the bridge change, especially the so-called bridge line change, and then to get the information of the bridge itself. So this is and also it's also possible to maintain such work with the industrial partner and know what happens for the bridge in the future, especially the 24 hours per day institute monitoring for the bridge, and then we know the traffic load and the healthy status of the bridge and so on, such informations. Okay, that's how I go to the acoustic sensing. So how can we use the acoustic sensing? Actually, we know that the FBGs. So the FBG array, we have keep the distance in between. If the distance between is changed, or there's a phase shift here, and then the two FBG arrays can have the interference, and then we can monitor the interface or the phase shift from the two areas, and then we can get the distributed acoustic sensing measurement. This is also I'll show you. But for that you have you have to get the fibry parallel structure. Then in that case we make the different grating. That means normally for the wavelength monitoring we use the very standard FBG, but for the distributed acoustic sensing we use the chirped FBG. That means the broadband FBG, and then you can get the interference from the broadband FBG arrays. That's the difference. Here is the OTDR measurement of the FBG arrays for the FBG with the FBG spacing is 5 millimeters, and the FBG, each FBG reflective is a full minus 45 dB, and you can see the spectrum here. And also we compared with the traditional fiber. There's a single mode fiber. For example, we use dust system, and this is the 1.7 kilometer traditional single mode fiber, and then later on we spliced with our 1.8 kilometer FBG arrays. If you use a single fiber, you see that this is a so-called scattered light. So normally people use a scattered Raman scattered singular like this, but if you have a very weak FBG arrays behind the FBG, then you can have this very strong reflectivity compared to the Raman scattering. Normally Raman scattering the level is 10 to the power minus 7 or minus 8. We have the reflectivity 10 to the power minus 4, minus 5, minus 6, and so on. So we can have the much stronger singular to noise ratio. Okay, this is one of the demonstration we use it in the subway in Wuhan. This is the tube of the subway, and then we, as you see here, we mounted our FBG arrays this side and also this side, and then you have the two FBG cables along the subway. When the train comes, then you know the information about the train information, and then they have many kind of possibility to get the information for example, especially with the big data and analyze, for example, vehicle health situation, and also the traffic measurement. Here there's a map you see here. This is a different subway, different train comes, and then you know the position and also the speed, and also what is really happening during. This is one of the subway system in Wuhan. We installed such system in this line, and then we can monitor the information. Okay, this is for one. And another application that you can also monitor, we use an FPG array. That means that each FPGs can be monitored. Based on the FPG information, we can also get other information such about the vehicle, also track health status. If it is normal, if this is normal spectrum like this, that's FPG arrays is normal one. But in case of problem, there are some kind of singular or noise singular. So in this, we catch this information, and this information can be analyzed later, and then based on such kind of information, they can get what happens with the metro, with what happens with the roads. Sometimes it depends on the situation. Could be problem with the train, or problem with the subway band itself. So that's the possibility for us. For example, here we can monitoring the train deformation as you can see here, and then we can have very pre-alarming or even have for the good condition and monitoring for such kind of vehicles. For example, here this is a normal envelope of the FPG singular, and then you can see here to the very standard. But for the abnormal envelope, you have the deformation of the spectral singular. In this case, we can monitor the track bed and also the train itself. And this is another application for the so-called monitoring of the structure. For example, here if there's a dream somewhere around the tree, and then you can get the different singular or different information good for really applications. But this is another also for the dust applications for the oil field. Then we can monitor the singular sounds from the underground, and then based on the DTG based dust get the informations with dust technology, and also we can also make the VSP logging for the oil field test, and then get the information based on the DAS technology with the drone power gratings. And also for the oil shed, we can for the preform monitoring for during the oil field treatments. And this is another example version of the so-called Huazhong fraction monitoring. That means if the fraction is very fraction, you have very strong signals, and you have very strong event there, and without and the normal things, this is something like kind of a background. But if you have the fracture, they have the strong intensity. And also we can monitor how it works. For example, here for the dense events with the strong signal, and if you stop the fracture, and then there's no signal, and then the fracture comes again, then you have also dense signals. In this sense, they can monitor the procedure to get an optimized system. And also, this is during the liquid feeding process, we can know how the liquid goes on the downhole, especially for the typical This is the typical DAS with the traditional single mode fiber, and this is our DAS with the ultra-weak FPG arrays. You can get different signals, but for the ultra-weak FPG arrays, since you can get a very clearly boundary compared to the traditional DAS technology. You can see here, they are connected, but they are more separated and so on. Well, you know, we use the FPG arrays, but you can measure in one cable, measure also the wavelengths, and also in between the FPG arrays, you can measure the distributed phase shift. That means wavelength measurement for temperature for straight, and phase shift measurement for the so-called acoustic sensing. So that means it's possible to measure distributed temperature sensing, distributed acoustic sensing, and distributed strain sensing in one system, especially in one cable. This is challenging for such kind of technology. We call it distributed acoustic sensing. But for sure, you have make different FPGs, and also you have make the different cable process inside. Here is a demonstration with the DTS measurement. That means we can measure the vibration, deformation, and also strain or temperature measurement just in one cable. This is and here we do it in the laboratory for the pipeline. For the pipeline monitoring, if that, for example, especially here in China, we have the hydrogen pipeline. The people are care about the leakage. If that leakage happens, there will be the signal, including the acoustic signal and also the temperature signal. So if you can measure temperature and acoustic signal in one system, in one measurement, that will be much more interesting for industry partner. This is our demonstration for the different. We just monitoring the system in the laboratory to know what happens with our cable for different leakage size and also leakage event. And also we just monitoring with the in-lab system with a different size and also with different protection for the cables and to get the different informations. Here is also a field test in one of the provinces of China. We measured the based on the distributed acoustic multiple parameter sensing. We can measure the temperature compared with the commercial DTS measurement. They are quite similar, but we can also measure distributed acoustic sensing. And this is also based on commercial acoustic. But there are two setups. For us, we just one. Just means two in one. Here is two separated system. Normally for this one, normally commercially it's based on the multi-mode fiber, and for the DAS for single mode fiber. For us, we all in this one fiber cable. And this is also the one of the field measurement in China, and also we can get the fraction, hydrogen fraction monitoring during walking, and to know what happens here, but we are not good at it. The signal analyze, but somebody will do the signal analyze. We just monitor what the signal that is, and also you see the temperature fractured. During the fracture processing, the temperature, because the water comes down to the downhole, and then the temperature measurement also. That means you can measure the temperature and you can measure the acoustic sensing in the same batch. Okay, I will mention a little about our other optical fiber sensing technology. As I mentioned before, we have make coating materials, sensitive materials, and the systems. And here is a demonstration of the fiber optic hydrogen sensors. We use specialty coatings of the sensing head, and then we use the traditional FPGs, and also with the based on the optical heating, and then we can get a very precise hydrogen measurement. And also use such kind of special coatings for the temperature and the relative heat management in one system. That's possible. And also this is we use especially the dual pass with the compensated system for the hydrogen measurement, and especially this is a very good result for the hydrogen measurement. It's with especially optical heating. We call it even with the self-compensated optical system, and this we can make such kind of prototype. It already goes to the market for really applications, and also we have such kind of system and on-site installation, on-site monitoring, and so on. Okay, finally, I made the conclusion that drone tower-based FPG arrays can enable single increase of multiple sensors labels, and the FPG array sensor could be a new choice for the distributed sensing, especially for multiple parameter sensing in one fiber. That means distributed multiple sensing with drone tower. It could be a new solution for many possible industrial applications. And finally, I would like to thank you for your attention.
So thank you, Professor Minghong. We have time for a very quick question from the audience.
Well, impressive talk. Thank you very much because it was amazing. Congratulations. And my question is related to the fabrication of the ultra-wide fiber Bragg gratings on the drone tower, because you said that the fiber, when you are fabricating the fiber gratings, well, the fiber is moving, and you implemented one technique to compensate these vibrations. How do you do it exactly?
Okay, that's a very good question. Sometimes this is somehow it's a secret.
He'll have to kill you.
I should mention a little bit, but I'll not go too much into details. Because the fiber is moving, right? Up, down, and then it's a very huge tower. Up, down, and then sometimes it has vibration, right? During the movement, especially the high speed, and it is per second several millimeters. So one question that you have to make is slow down, not that fast. The first slow down, and then the second you have to try to make we use kind of a damping, or we use a kind of the technology to maintain the strain as stable as before. That's two ways. Firstly, because we are not technical fiber, we don't care about too long. We don't, for example, for us, 10 kilometers is just enough. For many cases, 10 kilometers is enough. So we just speed up compared to the conventional fibers. And on the other side, we have to control the tension during the fiber running. That I will not say too much. Okay, thank you.
So thank you very much. We'll have time later for more questions during the coffee break, but we have to continue. So thank you, Professor Minghong, again.